Folks, are you ready? In this Chalk Talk, we are flying high and headed into the bright blue sky. But don't you worry, no tickets, tray tables, or seat assignments will be necessary. Because, my friends, we're talking about one of my all time favorite topics today: drone technologies. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Bob Card from onsemi and I explore the wide breadth of robotic and drone solutions offered by onsemi. We also explore the role that current sense amplifiers, image sensors, and inductive encoders play in these types of designs, and how you can utilize onsemi solutions for your next innovative drone application. And before we get started, don't forget to click that link. There you can find even more information about this topic from onsemi. Hi, Bob. Thank you so much for joining me.
Well, thanks for having me.
Absolutely. Okay, so Bob, we're talking all about drone applications today. So, first, talk to me about the drone and robotic solutions that onsemi offers.
Well, onsemi has a lot of semiconductor technology for the robotics and drone applications, and that includes intelligent power, intelligent sensing. And if you look at the top, you can see that you've got cobots, and then to the right, you've got AMRs or autonomous mobile robots, then you have drones, eVTOLs, and humanoids. If you go back to the AMRs, if you replace those wheels with propellers, a lot of the same technology that's in the AMR is also in the drone. And likewise, if you take the drone and replace those propellers with the joints in the humanoid, the brushless DC motors that are driving the propellers, they drive the joints, and then a lot of that technology transfers over as well. So we have a lot of intelligent power products that are listed here, as well as intelligent sensing. I'll go through a lot of these through this presentation. And this presentation really does focus on the applications and the technology that's more or less under the hood inside of a drone.
Okay, so Bob, the drone market globally is looking at a big increase in the coming years, right?
That's true. Drones are really growing a lot. If you look at the projected revenues, no matter what source you pick, and there's a bit of variation. In 2025, it's anywhere from 30 billion to 73 billion, but out to 2030 and 2033, it's growing at CAGRs or cumulative average growth rates of anywhere from 14% to 17%.
Bob, what markets are the biggest when it comes to drone applications?
The drone market is really about 48%, 50% is the military, which is captured in blue in the pie chart there. And that's followed by commercial in orange at 35% market share globally. And then finally in green, you've got the consumer market. And if you were to take that commercial application slice of the pie, which is at 35.5%, that's broken down into a number of different subsets. So we've got 6 of them listed here, and that includes construction, public safety and law enforcement, agriculture, oil and gas, mining, and others. And so you can see that there's a lot of different applications and there's a lot of diversity. In fact, there's a lot of use cases under each application. For example, for military, you've got intelligence, surveillance, and reconnaissance. Mapping and surveying is a popular use case for many of these applications. Target acquisition. If you go down to agriculture, you've got fertilizer and pest control spray. You've got crop health monitoring for detecting nutrient deficiencies or diseases, more mapping and survey, plant counting and density, livestock monitoring. If you go over to mining, quarries and aggregates, you've got mapping and surveying, safety and hazard determination. If you look at oil and gas, there's a whole bunch of inspection capabilities, infrastructure leaks, spoil or corrosion detection, environmental monitoring and logistics, early problem detection, pipeline storage leak inspections. And then for outdoor inspection, you've got power utility, pipeline, gas, lines. It just goes on, cranes, bridges, 4G, 5G towers, solar panels, wind turbines, maritime ports, and then photography, a whole thing on its own. Not to mention cinematography and filmmaking, a niche market, but you're seeing more and more drones being pulled into that market and application. And then you've got FPV drone sport racing. So FPV, or first person view, is an important acronym when referring to drones. The idea that the person, controlling the drone on the ground with the joystick and the panel can enjoy or have that experience or immersement and see exactly what the drone is seeing or what the camera of the drone is seeing. And that leads to drone racing leagues, racing communities, even a drone soccer team sport. You've also got plenty of outdoor applications, but also indoor warehouse for inspection, inventory, security and surveillance, environmental and forestry. Delivery is a big new application for drones, medical supplies, last mile, food, logistics, law enforcement for crime scene documentation, first responders, search and rescue, disaster response, construction, border patrol, public safety, even light shows, these swarm light show events where you replace fireworks with drone LEDs. It's just a myriad of different use cases and applications for drones.
So, Bob, drones are now being used for really cool light shows these days, and that market is growing as well, right?
Amelia, that's cool. Like, my kids, when they were little, I took them out to the beach where I live, for the 4th of July to watch the fireworks, and they were scared to death. And on top of that, our pets and our neighbors' pets get freaked out by fireworks. So there's this whole sort of, I don't know, like a migration of moving away from fireworks and into these swarm light shows with drones for events, sports events, any kind of holidays and that kind of thing. And it's a growing market. And what's cool about these swarm light shows is it's a pretty high tech thing. You've got to make sure all these drones are in the correct position to be able to create these patterns like the Statue of Liberty or the football player or the alien on the right. And it's really a lot of high tech effort goes into this. You could take this use case and apply it to mapping and surveying, right? And you may use one drone to do mapping and surveying, but you could put 4 or 8 drones in parallel flying together in uniform, sort of like the Blue Angels, and you could quadruple your throughput, which is very important for drones because drones are, it's all about the flight time. It's all about the time it's up in the air. So what I'd like to do is look at drone applications by power. And so I created this sort of number line on the x-axis at the bottom of the slide, which captures the drone total system power. What I mean by that, let's say you had 4 propellers and each propeller was driven by a brushless DC motor with 250 watts for each motor. That would be 1 kilowatt for the total power. So if you look on the bottom left, you can see I've got the nano drones, which can sit in your palm, the palm of your hand, from 0.1 watts to a little under 5 watts. Moving left to right, we've got the micro drones that go up to 50 to 100 watts, then the consumer drones up to 300 watts, then the commercial drones to a kilowatt to 5 kilowatt, and then you've got the manned drones, which are, the hover bike or the eVTOL, which is electric vertical takeoff and landing. And now you're talking tens of kilowatts, if not hundreds of kilowatts, and maybe even single megawatts. These eVTOLs are effectively an electric vehicle where you replace the traction inverters with motors to drive the propellers. So again, swapping the wheels for the propellers. It's kind of a common theme here. Now, what's cool and unique is when you take into account that military is just under 50% of the global market, that's a lot of drones. And typically in the past, many military products were purchased and supplied by specific military suppliers. And that's going through, in some countries, going through some changes where they're going more to the consumer market and commercial market to purchase these drones off the shelf as long as they meet certain requirements and to use those for the military as well. So it's a real bonanza for a lot of the commercial consumer micro drones, nano drones, and even the eVTOL companies that supply these products. You can go on their websites. They're very much actively promoting their drones for military as well.
So, can we take a closer look at a drone application?
Sure. So drone generic block diagram, you see here, you can see the main system on chip processor in gray in the middle. And that's really the brain of the drone. And I will say that many of these drones now are starting to, I would use the word evolve, into using processors that have some sort of AI capability. It used to be, you'd fly the drone, the person down below would fly the drone. And now they want these drones to be thinking a little bit on their own. They want to be able to avoid power lines. They want to be able to, do certain types of maneuvering, think on their own. So you're seeing more and more processors that have AI inside. On the left, you can see for this generic drone block diagram, on the left, you've got your wireless connectivity with Wi-Fi, 4G, 5G, and GPS. And then Up on the top left, you see that lithium ion battery, and that's typically a lithium polymer electrolyte. And that's because it has the highest energy density. If you have an autonomous mobile robot that's battery powered and the battery runs out, it just stops, right? But if you've got a drone, 80 feet in the air and the battery dies, it's a different story, right? So you need to have the most efficient products and maximize the amount of all those coulombs in that battery to go to the propellers, the brushless DC motor for the propellers. So up there, I've also got an E-fuse in between the propellers and the battery pack. Arguably like 95% of the energy is going to go into the propellers. And then we also need to supply all the circuitry that you see in orange here. And actually everything in orange is what onsemi provides for this market. And you need a very efficient DC to DC to create the power tree to be able to power the double EEPROM memory, ambient light sensor, ultrasonic LiDAR, pressure sensor, visual navigation systems, the gimbal circuitry. There could be LiDAR in there, or SWIR, which is an acronym for shortwave infrared, LED drivers, the BLDC for the yaw, pitch, and roll inside the gimbal, as well as many of the other circuitry that you see here.
So, Bob, what does the power distribution look like in an application like this?
Well, the power distributions, it's unique because you got to really consider the battery pack. And so that's why on the left, I've captured in blue font. These drones, just like power tools and autonomous mobile robots and humanoids, are powered by battery packs. And it could be one cell, which I have 1S, which would be 3 volts to 4.2 volts for a lithium polymer typically. And 3 volts is basically 0% state of charge, 4.2 would be 100% state of charge, and 3.7 volts would be roughly 50% state of charge. However, you can stack them in series, 2S, 4S, 6S, 8S, and 10S, where 10S, now your battery range is 30 volts to 42 volts, empty to full. And so that's going to drive your power tree because your power tree needs to be very cognizant of the input voltage. And you can also add more power in terms of amp hours or watt hours, as I've captured down below on the left, is by adding more cells in parallel. And so anyway, now that you've got this, sort of like varying voltage, right, that's changing depending on the state of charge of your battery pack, that needs to feed into some sort of a step down synchronous buck, which I use the fan 65,000 family, the fan 65,008. And that allows you to efficiently, it's got an input range of VN of 4.5 to 65 volts. So it's very conducive to up to 10S battery packs. And then you can buck that down to 5 volt rails, 12 volt rails, 3.3 volt rails, 1.8 volt rails, and so on, and power all that circuitry that I have captured in this diagram.
So, Bob, let's also talk about some of the solutions you mentioned.
Sure. So specifically that fan 65,000 family, we have 3 devices. We have the fan 65,004C, which is a 6 amp device. We have the 5A or B, which is an 8 amp device. And we have the 8B, which is a 10 amp device. They all have the same footprint in a PQFN 6x6 35 lead package, integrated high side, low side switches. So it's a full synchronous buck. And it takes an input, as I mentioned before, of 4.5 volts to 65 volts with an output voltage of 0.6 volts to 55 volts. So it's very, very flexible with respect to taking an input from lithium ion stack cells. It's got a programmable frequency of 100 kilohertz to 1 megahertz with all the protections and short circuit and thermal shutdown that you require for an application like drones. And so the fan 65,000, what I really like about this is the efficiency. For a 40 volt in, and on the y-axis I have efficiency, on the x-axis I have the load current in amps, you can see that for 24 volt and 19 volt output, the efficiency is well above 97%. And for a 12 volt output, the efficiency is higher than 96%. And so what that means is the higher efficiency you have, the better you're using the battery, the more you're optimizing the energy, the coulombs that are in the battery, which means you can have longer flight time. If you use inefficient DC to DC, you're going to have shorter flight time. So the efficiencies of your bucks and really all the circuitry you put into the drone benefits the flight time of the drone. We also have a great 4-channel E-fuse. You got to always be thinking about protection. And we have the NIS 3071 E-fuse. The V stands for automotive qualified. So we have industrial qualified and automotive. And this has 4 independent 2.5 amp channels that you can see on the bottom right. You could have one source coming in from 8 volt to 60 volts, and you can support up to 4 individual 2.5 amp loads for protection, up to 150 watts. Or in the middle at the bottom, this is really cool, scalable device. You could have 2 5 amp loads, or on the far left on the bottom, you can have one 10 amp load. So you can junction these channels. You can gang these channels up. Each channel has a separate enable pin. You have a fault output, which follows this fault truth table. And there's also an ILM input where you can set the limit of each channel. Right now, it's by default 2.5 amps, but you can vary those limits depending on the resistor tied on the ILM input. On this slide, figure 5 on the left is the MT3 and the MT4 version. And figure 6 on the right is the MT5 and the MT6 version of the 3071. So we have 4 versions. So on the left, the MT3 and MT4, if your ILM resistor is from 0 to 60 k ohm, then your ILM range is 1 amp to 2.5 amps. For the MT5 and the MT6 versions on figure 6, if the RLM is from 50K to 300K, then your range for the ILM is 200 milliamps to 1 amp. So very, very flexible type of product. You can vary the ILM on each of these devices.
All right. So we also need to talk about propeller BLDC protection, right?
Yes, there's a lot of current going into these propellers, the brushless DC motors for the propellers. That's how the thing flies. Some of these drones have 4 propellers, some have 8, some even have 12. So there's a lot of energy in there. If there's some kind of malfunction in one of those propellers, you don't want it to shut the whole thing down, the whole drone down, and damage the battery or any other circuitry. So you can use this NIS 3071 to protect these individual propellers. I just drew it out here just to view this.
Okay. So can you walk me through what a propeller BLDC would look like?
I sure can, Amelia. So you can see in this block diagram on the far right in gray, I have the 3-phase BLDC motor, and there's a U phase and a V phase and a W phase. And each phase has a high side, low side switch moving right to left. And that high side, low side switch is how you inject energy into each phase to make that motor spin. And then moving further to the left, I have the NCD 83591 3-phase 60-volt gate driver, and it's responsible for turning those switches on and off in the proper fashion to spin that motor in an optimal way. And moving right to left, we've got the processor there, and that processor drives the gate driver with pulse width modulation or duty cycling. And it's following some sort of commutation algorithm to spin that motor for the propeller efficiently. And it could be something simple like a trapezoidal or something more complex like sinusoidal or field-oriented control. Meanwhile, you can run that motor what's called sensorlessly, or you can have sensors in the motor. They can be Hall, or in this case, I've got inductive position sensors with the NCS 32100 or the NCV 77320. And what those sensors do is they tell the processor where the rotor is in its spin to help it optimize its commutation algorithm for spinning the motor. Meanwhile, on the bottom left, I've got the NCN 26010 10-base T1S controller. That's a CAN replacement. You can use a CAN controller as well for a multi-drop protocol for wired communication. I'll talk more about this later. But we do recommend transitioning to 10-base T1S because you can go 2 to 3 times faster than CAN over the same 2 wires, and you also have Ethernet. We also have a double EEPROM down there, the N24664, and above, we have the protection that we mentioned earlier, as well as 2 LDOs, the NCP 737s. Those are newer LDOs. We just released those a few months ago. And those take a wide input of 3 to 65 volts to power the inductive position sensor, as well as the processor and the 10-base T1S.
So, Bob, can we also talk a bit more about those T10 LV MOSFETs you talked about?
Sure, those low voltage MOSFETs, which were in the previous slide for the brushless DC motor, those are the high side, low side switches. There's 2 for each winding, so a total of 6. And what you're really shooting for is a low RDS on for those low voltage MOSFETs to be able to reduce your conduction losses and efficiently spin that motor. Again, it's all about having an efficient solution for all these different subsystems within the drone to maximize your flight time. And so you can see the y-axis is the breakdown voltage. We have 25 volt, 40 volt, and 80 volt, blue, pink, and orange. And the x-axis is the RDS on with the VGS of 10 volts or a gate to source voltage of 10 volts. And you can see on the right-hand side, on the bottom, that's 1 milliohm. So we have a number of devices for 80, 40, and 25 volts that are below 1 milliohm. We actually have, what's the lowest one? Yeah, a 0.49 milliohm for 40 volt. That's an excellent solution for BLDC for propellers of drones. Lower RDS on means higher efficiency during your conduction losses. And then you move right to left, we have 1 milliohm, 2, 3, 4, and 5 milliohm. So a really wide selection. onsemi is a leader in low voltage, as well as many of these technologies for drones, but a leader in low voltage MOSFETs.
So, Bob, you mentioned a 60-volt three-phase gate driver as well, right? So, walk me through the benefits we're looking at here.
Yeah, that NCD 83591 60-volt gate driver, what's nice about that is a three-phase gate driver. So for one gate driver IC, you drive all 6 switches to be able to spin that brushless DC motor. So it's a nice advantage of that. What's also nice about this device is that there's 2 resistors on the input of the device. It's a little small resistor ladder. And depending on the values of those resistors, it configures the gate driver from 5 milliamps to 250 milliamps. So you can control the gate drive that way. It has shoot-through protection. There's an embedded high-gain bandwidth op-amp that can measure the I-sense of the phases. It's got under-voltage lockout. It can go up to 30 kilohertz motor pulse width modulation frequency. Its junction temperature range is minus 40 degrees C to 150. And it all comes in a very small 24-pin 4x4 millimeter QFN. So we have many more gate drivers beyond the NCD 83591, as you can see at the bottom left. We have many more gate drivers that I captured on this plot. Everything in orange means it's a 3-half bridge gate driver, meaning you only need one of them to drive the BLDC with the T10s MOSFETs. Or you can use the grays, which are single half bridge gate drivers. You would need 3 of those. So I put them on this plot because the x-axis captures the gate drive source and sink in amps, and the y-axis is the voltage, that rating. And so you can use the fan 8811 if you need more gate drive with 3 amps and 6 amps, or the NCP 51513, which is 120 volts, 2 amps and 3 amps. So we have a lot of selections and options if you want to build, for your BLDC.
So, what about current sense amplifiers? What kind of solutions does onsemi offer here for drone applications?
We have a full family of current sense amplifiers. And what's nice about the current sense amplifiers is they're op amps with integrated feedback resistors that are trimmed at the factory. So it's a lot easier to use. It's a lot more accurate. Moving left to right, these different groups, we have common mode of 26 volt. Then moving to the right, we have 3 devices that have a 40 volt common mode. And then moving to the right, we have 2 devices with 80 volt common mode with excellent accuracy or gain error from minus 40 degrees C to 125 degrees C. Very, very excellent accuracy products. Some, 0.3% to name a couple, and very low voltage offsets as well in the tens of microvolts.
So, Bob, let's also discuss navigation systems. So, we're looking at 2 different kinds of vision systems for drone applications, right?
Amelia, that's true. Up at the top, you've got your visual navigation system, or VNS. And that's where you've got cameras and other sensors that are basically there to, navigate the device, avoid collisions, and interact or perform algorithms for SLAM, which is simultaneous localization and mapping, using other sensors. And you could have up to 8 cameras just for the navigation. And meanwhile, and it's actually optional, you could have a gimbal. And that gimbal hangs from below. Many times it attaches to the drone, and they're interchangeable. And these gimbals are kind of special. They really specialize in the first person view, or FPV. And that's where the drone pilot sees what the camera sees in real time, enhancing immersive control and maneuverability. But it's also a place like, you can see in the picture on the bottom left where it might be, mapping. And so it may use a LiDAR or a high resolution camera or a thermal camera. And the whole point there is that gimbal, these drones are outside flying around in the wind and the rain and the snow. They've got their own vibration from the propellers. And this imaging in the gimbal really wants to be stable. And so they add these 3 BLDCs for yaw, pitch, and roll control, along with a gyro accelerometer, magnometer, and an absolute encoder. So it's a bit of a boutique thing where you really want to have high quality imaging to be able to perform the FPV or, tracking or thermal imaging or whatever it is that you want to do.
So, what kind of image and IR sensors does onsemi offer for these kinds of systems?
Well, onsemi is really a leader in image sensors. We have a very wide portfolio and wide breadth of image sensors and IR sensors. Up at the top, in the first column, it captures the camera type. So you've got FPV, which is first person view. Typically, you would have that in the gimbal, but if you don't have a gimbal, it could potentially be higher above. But typically in the gimbal, and we've got 8 megapixel, 12 megapixel, and 20 megapixel options with varying pixel sizes. Shutter types, we have rolling shutter there, as well as the maximum frames per second, max dynamic range, which how well it develops an image with very, very low light, the scaler, the smart ROI or region of interest, context switching, and subsampling modes. And further down, back to the first column, you've got the VNS cameras, what we recommend for the navigation. And those are 1 megapixel, 2, 3, and 8 megapixel. Further down, we've got the row for IR. That includes SWIR cameras. And then also at the bottom, we've got the depth sensing. So we also have this new product called the AF0130 and 131. And what that does is it's a 1.3 megapixel camera. Not only does it measure width and height, but it also measures the depth. It uses what we call ITOF or indirect time of flight and gives you the best of both worlds. It gives you a camera image as well as measuring the depth. And so you can do depth sensing as well. And so this slide here just captures some of the LDOs and bucks that we might use to power our image sensors. And this table right here assumes a 5-volt incoming rail, which is captured in the block diagram on the right. And then above, we have a link to our website where we list many of these tables and block diagrams for all 11 of these Hyperlux image sensors, where we also share the power tree we would use for 5 volts, 18 volts, and 48 volts. We also partner with companies that make the camera modules or kits. Leopard's one example. And here's 3 of their products using our AR0234 CS 2.3 megapixel image sensor with global shutter. And on the right, 2 of the products that use our 8.3 megapixel with rolling shutter. So just give you an example. Some customers don't want to do the whole camera module themselves. They don't want to do it discreetly. They'd rather buy a module, and we partner with many different module makers. And one thing about the gimbal block diagram, it's a very specialized piece of hardware and software because it needs to maintain significant stability in harsh environments, right? So it's got this yaw, pitch, and roll capability, these 3 motors, where it moves these motors to keep an even, steady image while the drone above it could be vibrating or moving around because of wind or rain or snow or what have you. And one of the big enablers for that high stability accuracy is the NCS 32100 encoder that I have drawn below each BLDC, yaw, pitch, and roll. And that feeds back to the MCU that typically is running field-oriented control. These motors are boutique motors. They're specialized. So the motors themselves don't vibrate too much to cause any, buzzing or movement when you're trying to do this high-quality imaging. And it's all tied into the inertial measurement unit with the accelerometer, magnometer, and gyro, with the double EEPROM and the pressure sensor and all these other products all kind of tie in to make this a very, very accurate solution.
So, talk to me about why we should use inductive encoders over optical or magnetic solutions.
Sure, that's exactly right. There's different types of encoders for determining where the rotor is in a brushless DC motor. You can use optical or magnetic or inductive. We like the inductive because it has low sensitivity to vibration and contaminants. That includes dust, water, oil, metal particles. It also has a low component count and no rare earth metals, i.e. magnets. It has very robust repeatability and temperature and sensitivity, but number one is the lightweight, okay? And because these inductive encoders, which is our focus, uses these PC boards for the stator and the rotor, it's much lighter than the magnetic and the optical. And weight is so important for drones, as you can imagine. So the NCS 32100 offers a position accuracy at 13.8 degrees mechanical rotation, or 50 arcsecs, which is world-class performance. And it does that by using these 2 rotor and stator PCBs. The rotor PCB is attached to the shaft of the motor, and the stator PCB is stationary where the product exists. And as that rotor PCB spins, we have a free PCB design tool online where you can design the rotor and stator and the different patterns on there. And with our specialty with this kind of product, we can achieve this really high accuracy. And this is also an absolute sensor as well.
So, Bob, what kind of solutions does onsemi offer when it comes to inductive positioning?
Well, we have the NCS 32100 in the top row of this table, which I mentioned above, but we also have the NCV 77320, which is state machine based. The NCS 32100 is MCU based. It's got a M0 plus processor inside. So that bottom row, it's not as accurate as the NCS 32100, but it has a wider temperature range. It goes 150 C versus 85 degrees C. And it's also state machine based. And I've had some customers reach out to me and say, look, for a security reason, we want to reduce the number of MCUs because that's a vulnerability for hacking code. So that's one instance where, they do sometimes look for state machine solutions versus an MCU solution. Not always, but I've heard it here and there. We also have a full selection of double EEPROMs, which are electrically erasable, programmable read-only memory, which from 2 KB all the way to 256 KB using either I2C or SPI interface. So this is basically your non-volatile memory. MCUs, they want to wake up and have some code to run on. So an external double EEPROM is always handy. And we have a full solution of that. And you'll note that we have 1 million program erase cycle capability or robustness with 100-year data retention robustness as well.
So, Bob, we should also talk about LED lighting for these drone applications, right?
That's very true. And that's where these swarm light shows come through using drones. As I mentioned earlier, you have to position these drones in a certain position, obviously, to create these wonderful colored patterns. And you're going to need really good LED drivers. You need to develop or drive those lumens, and you need to do it efficiently. And so onsemi is a leader in automotive lighting. We have been for decades. And this is another application that's a perfect fit for the automotive LED lighting. And so what we have is for front lighting, automotive LED drivers, we have SPI multi-channel, which includes boosts and dual buck, multi-phase boosts, 2-phase and 3-phase, as well as matrix beam controllers. And the point is all these LED controllers, which are really designed for automotive, but it's a perfect fit for drones, they have very wide inputs. The VN inputs are very wide. Some are 6 volts to 67 volts, other are 4 to 40 volts. And anytime you see those wide inputs, it's a really good fit for anything that's powered by lithium ion battery packs, right? Because those batteries, once you're in mission mode, they never stay the same voltage, right? You might have a fully charged battery, and by the time you're done with your 20-minute flight time, it's down to, 10%. So that voltage is changing. So you want your electronics to be happy with that. You not have to add DC to DCs. And these can literally run directly right off the battery packs. Anytime you do that, it's more efficient. So we've got the front lighting, and the next slide, we have the rear lighting, which just has more capabilities. We have 8-channel, 12-channel lighting. A lot of these, they have fault detection. They have built-in diagnostics, open short LED string diagnostics. And we also have what are called CCRs, or constant current regulators, as well. So those are low-cost solutions. So a lot of different options for lighting. More specifically, the NCV 7685, that's our 12-channel LED driver. That's one of our leading selling LED drivers for automotive, which is a perfect fit for these swarm drone light shows. And this can run either in MCU mode across I2C, or it can run in standalone mode. It has 12 common current programmable sources up to 60 milliamps each. Each one is independently PWM'd or duty cycled to control the dimming across I2C. And it also has open LED string diagnostics. So very robust solution for your drones. And then we also have the NCV 78514. And what makes this LED driver unique is it's got a 4-phase H-bridge topology. And what that means is it automatically adapts the output voltage, or actually keeps the output voltage constant, while the input voltage can go up and down from 5 to 20 volts. So it autonomously is either a buck or a boost, depending on the input voltage, and puts out that 60-volt output, powering up to 20 LEDs.
So, Bob, what about wired communication? Let's talk more about that aspect of these designs.
So you have wired communication throughout a drone, and a lot of your image sensors, which have, megapixels. That's going to need a dedicated high bandwidth communication link, typically point to point. That could be a gigabit Ethernet or some sort of serializer, deserializer solution. However, you've got other things that need to communicate with one another and a system on chip flight control device like the BLDC, the LEDs, the ultrasonic sensors, and many other sensors where you don't need high bandwidth, but you need to communicate. And you want to do that wired. And so CAN bus is a very popular solution because it's a multi-drop solution. It's not point to point, it's multi-drop. So you can connect many different devices off sort of one run of wiring, and it's unshielded twisted pair. So it's very lightweight. It's only 2 wires, low cost, low weight, and takes up a lot less room. All of those things are important. But you can also replace the CAN bus with 10 base T1S, and you can run 2 to 3 times faster than CAN over the same 2 wires. We call it single pair Ethernet for the Ethernet world. So you get the best of both worlds, and now you're doing Ethernet instead of CAN. So there's an advantage there. And we have 2 devices for that. The first device is the NCN 26010 10 base T1S industrial Ethernet controller. It has a SPI bus to interact with a companion MCU, where that companion MCU would send it the Ethernet frames. And then this sends the frames out across a single pair Ethernet on the far right. And this includes a MAC-PHY as well as a PLCA, which is a physical air collision avoidance. We also have another part called the NCN 26000, where we jettison the Ethernet MAC because sometimes the MCUs already have that. That would be redundancy. And so for environments or applications where you already have an MCU with a MAC, we have the NCN 26000, which does not have a MAC. So 2 solutions for 10 base T1S. However, if you want to just go to CAN, which many customers prefer, they're used to it, we have a full portfolio of existing CAN transceivers. That's for CAN and CAN FD. We have singles, we have duals, and we have CAN SBC, or a system basis chip, which are CAN FD devices that also have integrated LDOs and DC to DCs in order to power other devices that are close to that controller.
Okay, so let's talk about those ultrasonic sensors as well.
Yeah, we have the NCV 75215. It's an ultrasonic sensor. It was designed for automotive park assist, but it can definitely apply and be used in drones. And this particular device, the measurement distance range is from 0.25 meters to 4.5 meters, depending on external parts. And the transducer center frequency range is from 35 to 90 kilohertz. And so in the next slide, you can see, how it sits inside of a module. There's many pieces to it, one of which is the ultrasonic piezoelectric transducer, which this device, basically vibrates. That creates a transmit wave, AM modulated wave. It leaves the device and it hits an obstacle. And then there's a reflective wave. We measure that reflective wave to measure the time of flight. And you can see where a drone may be attempting to land, and an ultrasonic sensor can tell the processor how close it is to the ground. Or if you've got these swarm light shows, all these drones need to be in perfect uniform locations, very well defined, and they can't be moving left to the right. And so they're going to use a lot of sensor fusion to be able to achieve, the Statue of Liberty pattern or the UFO alien pattern, if you will. And so each one of these drones has its own position, sort of like when you look at a parade and you see the marching band. It's a similar kind of thing. Everybody has their place. And so ultrasonic helps with the sensor fusion to be able to accomplish this very, very cool application situation.
All right, so what about the pressure sensing solutions?
Right. Pressure sensing is an important aspect in drones. And we offer the NCV 7192. It's actually a signal conditioning device. It pairs with a PWM, a PWB, or a piezo-resistive Wheatstone bridge. And so basically you can see that it's a transducer. And so our part, the NCV 7192, it biases the PWB. And if there's no pressure on the PWB, you get 0 millivolts out. But once you start putting pressure on the PWB, then you get tens of millivolts out, or maybe 100 millivolts out, and that goes into the NCV 7192, and it conditions that signal. It amplifies it, but it also takes out a lot of the error and nonlinearity and gives you a nice proportional analog output of 5 volts, or a digital output called SENT, which is an automotive protocol, to an MCU, and then that MCU can measure force, displacement, pressure, barometer, altimeter, torque, weight, compression, or strain. All applicable measurements that can be used inside of a drone.
Absolutely. Now, of course, we also need to talk about the battery charger as well, right?
That's right. And, we have a block diagram here for a wide bandgap 3 kilowatt power supply for battery charging. And this particular wide bandgap uses silicon carbide. And so if you look at the block diagram on the top left, the AC input's 85 to 260 volts. The DC output is 48 volts at 62.5 amps. That output goes into the gray box on the bottom right that connects to the battery pack. That's called the CCCV charge profile control. And that follows the CCCV autonomous charging profile I have on the bottom left with the 4 endpoints. That's how you properly charge, one way to properly charge lithium ion. And now back to the block diagram. At the input, we give at the NCP1681 totem pole PFC controller. And you can see that's controlling the slow leg and fast leg half bridges, essentially. And the slow leg runs at the line frequency of 50 or 60 hertz, and the slow leg uses silicon junction. The fast leg is where we put the silicon carbide, and the fast leg runs from 30 kilohertz to 130 kilohertz, I believe. Don't quote me on that, but much faster. And by doing that through an isolated gate driver, the 1681 totem pole PFC, using that, you can jettison the full wave rectifier you typically have for a power supply. That saves on the form factor. It allows you to reduce the form factor, and it increases the efficiency because using the full wave rectifier diodes are a lot less efficient. Then you have the NCP4390 secondary side LLC controller, and it's controlling the full bridge on the secondary side, as well as 2 more Elite SiC MOSFETs with another 5K isolated gate driver. And that NCP4390, because it's an LLC controller, can go much faster. And because it can go much faster, you can use a smaller transformer, smaller capacitors, smaller inductors. So the form factor for any given power gets reduced greatly. If we take a closer look at the NCP1681 totem pole PFC controller, it's a totem pole controller, so you can jettison the full wave rectifier, but it's also a PFC or power factor corrector, which what it does is as these loads vary, the loads can cause the current and voltage to go out of phase. So a PFC brings the voltage and current back in phase, and it does it with either CRM or CCM, which is what we call multi-mode. And it's a state machine-based device, so you don't have to write any code. Some of our competitors have code-based totem pole PFCs. This is state machine-based. A lot of power people don't like to write code. It's a great fit. And we also have the NCP 4390. It's also a V version for automotive qualified. And that's a great device because it controls the secondary side full bridge and the primary side half bridge, and goes up to 690 kilohertz for reducing, the faster you go, the more you can reduce the size of the capacitors and transformer and inductors. So it's a nice value advantage that way.
So, can we also talk about the BLE subsystem as well?
Sure. We offer the RSL15 BLE device. The RSL15 supports angle of arrival and angle of departure. And so if you want to use angle of arrival, that works for real-time location services where the transmitter is a single antenna, typically moving, and it generates the continuous tone extension. And the receiver is a switching antenna array, typically fixed, where it captures the IQ samples and calculates the real-time locations of the device. In contrast, you can use AOD, where that's really more applicable for indoor positioning systems, where the transmitter is a switching antenna array, typically fixed, generating the continuous tones, and the receiver is a single antenna, typically moving, and captures the IQ samples. And we partnered with Unikey, who developed the algorithm for the locations, both IPS and RTLS, and using our RSL15 BLE device. And we also partnered with Murata to create, using RSL15, the BLE 5.2 module, where Murata integrates our RSL15 along with the inductor, the crystals, the matching circuit, and the antenna. So a full solution. Many customers prefer this option because it's faster to market. They don't have to do the antenna design, which ain't nothing. So we partnered with Murata for that as well.
All right. Well, Bob, I think that's all I have time for today. Thank you so much for joining me.
Hey, Amelia, like always, I appreciate it. Thank you very, very much.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from onsemi. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EEJournal.